All right. Good afternoon, everyone. Hope you all stay home and stay warm. So we have the class online because of the weather. We're going to talk about the indeterminate bars as mentioned last time. All right. So last time we talked about the non-uniform bars, right? So just a quick review. If you have a bar that's either with a changing area or changing material modulus, right? Or changing internal force, then we say the bar is not uniform. So to determine its elongation, we have to make separate segment, right? So calculate the deformation of each segment, and then we add them together. Okay, so basically, the key step is to make a cut, right? So for example, in this case, you cut in the first segment here, right? And then you also cut in the second segment. So here, through this cut, and then this cut, right? So then you draw the free body diagram, and then write the equation of equilibrium about all these free body diagrams. And then you get the equation, so you can find out the Ni. So once you have Ni, right? So for each bar, their elongation, right, is there uniform. So therefore, you can use the uniform equation we got last time. So you calculate the elongation of each one, and then you just add all of them together. So that's how we determine the total elongations, right? So the key is make the cut free body diagram. All right, and equation. Okay, so today we're going to look at this situation when things become indeterminate. Okay, let's see what we mean by indeterminate. Okay, let's say we have the same bar I just showed you. Now, instead of free on the right, now I have a wall, right? I build a wall on the right to support it. So the bar basically attached to the wall on both sides, the point A and B. Okay, so it's still the same load, P1, 5K, still applying in the middle. Okay, in this case, if I want to figure out the elongation of each bar, or I want to figure out how much the middle point C moves if I apply the load P1 there, right? So we can basically do the same thing, right? For example, we can make a cut, right? And make a cut here. Okay, so with this one, right? So you can, let's say this is the first segment and this is the second segment. So therefore I call this N1 and then this one will be N2, right? Okay, so let me change my pen to different color. All right, so then what you need to do is right after the cut, right, you draw the free body diagram. Okay, so for example, I can draw this one. So I have this side here, this is the cut. Okay, so this is the wall, so this is the point A. So now I have a reaction right here, so that's RA. Okay, so this is what I'm looking for, so it's N1. Okay, or I can draw the free body diagram this way, right? The middle here, middle part, so this is the cut. Okay, so I have the load P1 applying here. So here I have the N1. Okay, I don't know it's tension or compression, so I just assume everything's positive. So it's tension, right? Everyone can stretch it. So therefore, I have N1 and this will be N2, right? If you say, yeah, I can also draw this one on the right. So this portion here, right? This is the wall, and so this is point B, right? So point C is here. Okay, so then this will be N2 as well, right? Okay, so here I have the RB. Okay. If you don't know, you can just assume it's to the right, right? Can be tension. Let's assume it's tension here, just for easy, without thinking, right? We don't need to think. So this will be the RA. So it's going this way. Sorry, RB, right? Okay. So I just assume everywhere is tension. Okay, now with this three free body diagram, so I can write the equation about it, right? So the first one I can get, so if I write it here, so this is basically the free body diagram I already get. Of course, someone can say, yeah, I can also draw the whole system, right? So I can draw here, right, RA, and here, then I have this RB, right? Okay, then that's for the whole body, right? So basically, you can draw 4 different free body diagrams. Okay, actually, you can draw more if you want. You can draw from the N1 this part to wholly to this part, right? That's fine, but I think you don't need that many, right? So let's say if for this one we get as a equation of equilibrium. Let's write it here. Okay, so what do we get? Negative RA. And that plus P1, okay, and then plus RB equals 0. Okay, so from here I get RB minus RA, right? Actually, the other way, it's RA minus RB equals to P1. P1 is known, right? Load is known. Okay. Now from this one, this free body diagram, I can write the equation of equilibrium. So what I have will be negative RA, right? For this one, equation of equilibrium. So then plus N1 equals 0. Okay. So I have N1 is basically RA. Now for this one, I can write the equation of equilibrium. So negative N1 plus P1 and then plus N2 equals 0. Okay, for the last free body diagram here, I can write negative N2, then plus, right, RB equals 0. Okay, so basically here, this one gave me N2 is equal to RB. Okay, this one gave me, say, okay, so the N1 minus N2 equals to P1, right? Okay, so now we have 1, 2, 3, 4 equations, right? How many unknowns? Okay, so RA, RB, N1,
4
N2,
unknowns.
4 unknowns. Okay, well, seems we can solve it. But actually, no. The reason is they are not independent. It's like you can draw more free body diagram. For example, you can draw this one here and one here, right? So to here and then all the way to B. Okay, so you have RB here, and then you have P1 here. You have this N1 here, right? So you get what? You get N1 negative plus P1 plus RB equals 0, right? And that gives you N1 minus RB equals to P1. Well, I can get this same equation from the one I already have, right? So it basically, right? So let's say you have N1 equals RA, N2 equals RB, right? So you have the RA plus, RA. So it's RA minus RB. I'm just rewrite this equation here, equals P1, right? And this one versus this one, it's basically the same thing. Because N1 is RA, N2 is RB, right? So they're not independent, they just repeating each other, right? So the independent, you have unknown, you basically 2. Fundamentally, you have 2 unknown. Either you call RA, RB, right? Or it's just N1, N2. But how many independent equations you have? In this case, we know from the the basic theory, right? Statics. Let me get the phone. Sorry about that. That's a problem from talking from home. All right. Okay, so we basically have one fundamental have one equation. That's sigma fx equals 0, right? If you look at this here. So fundamentally have one equation there. And we have two unknowns. So we cannot determine. Right? So you cannot, based on equation, you cannot find out N1, N2, because there are two unknown. And you only have one equation. That's it. The key equation, just one, right? You add RA, RB in, right? But then you add more unknown with additional equation. It's fundamentally the same because RA is N1, RB is. Okay. So we call this kind of problem, that's the indeterminate. Because you cannot because you cannot determine the internal load or some of the reactions, right? RARB, two reactions from the equation of equilibrium alone. Okay, so that's what we mean by indeterminate problems. All right. Okay, so that's the definition. All right. We're going to talk about more next, but here is two things. One is why have this indeterminate, and that's because when you build a structure, you oftentimes want more support, more stable, or for functional purpose. You want build a bar between these two walls, right? So people can pull or connect it, right? Or can walk like a bridge or something, right? So there are oftentimes either function need or you add additional support to make the structure stronger. Okay. Now, second is for this kind of structure, indeterminate. Okay. How can we solve it? For example, for this bar. Okay. Anyone got a suggestion? How can we find out N1, N2 in this case? We only have one equation. Remember, we talk about now since we look at the bars, they're soft, right? In our eye now, since all deformable. So basically, we need to look at how they deform based on the deformation that may provide us some additional information, right? Okay, so for example, right, in this case here, right, if we, there are two ways. One is if you think it, you apply load in the middle, right? So what you do here is you are pulling, right, this point here to the right, okay? If the structure is safe, right, we'll talk about the small deformation, safe situation, right? Then if you pull this point C with a load, so this C is going to move to the right a little bit because the bar AC and the CB, they are all elastic, they're all deformable, right? So this point going to move a small distance, let's call it delta C, somewhere to somewhere here, right? Okay, then what happened to these two bars? So this two bar AEC must be stretched a little bit longer, and the CB must be compressed a little bit shorter, right? So what you have is basically we say the delta C, okay, should equal to the elongation of the first bar or equal to the shrinkage of the second bar. Right? That's how this thing can happen, right? Only this, that's, you allow this point to move, right? It deform. Okay. That's one way of thinking about it. Okay. The second way we can think about it, look at this one is, okay, now you have this bar here. We draw all this free body diagram. So this is for part one, right? part 2, and so you have 2 segments, 1 and 2. So what's the total elongation? The delta total, okay, that is displacement at point B, okay, that must equal to what? The first one plus the second one, but must be equal to 0, right? So if you imagine you have this load, so you have this P1 applying here, right? And then you have the RB applying here. So this is like a non-uniform bar, right? You have a P1 applying in the middle and then RB applying in the end, right? So imagine you have the right load RB there, then the pulling and the pushing, they all add together, makes this point perfectly not moving, right? Because otherwise you apply too much RB, then you move to the wall. That's impossible, right? The wall will push it back, so your RB will decrease, right? If you pull too small, there is a gap, then you're not, not reach the wall. So therefore you have to increase RB until this end reach the wall. So basically, right, we have this either 1 or 2, right? That's our condition. Okay, so with that, okay, what we are looking at is basically look at the deformation, right? How the deformation, right, is forming with the structure, right? So here we find out either you say the elongation of the first one plus the elongation of second segment, they add together, total should be 0, right? Or you say, oh, the value of them must be equal because that's how the middle point move. Okay. So basically now we talk about the relation, right? How the first one move, how the second one move, right? How they can match each other, or what we call how they can be compatible to each other. Okay, so that's the relation, right, about the deformation, the geometric relation about its deformation, and we call this compatibility equation, and that gives us additional relation, right, as I show here, either this one or this one. Okay, so that gives us additional relation, and we can use that. Now you have an additional equation, so you can combine with the equation of equilibrium we got here, right? So now you have additional equation, combine these two, now you have 2 unknowns, so maybe you can solve it, right? So that's the way of thinking, right? So when you have a deformable system, so we look at the deformation of each one and then see how they are compatible to each other, right? How they match each other, right? How they kind of accommodate each other, and then generate that deformation for the system. Okay, so the so-called compatibility equation. So that's what we do for the indeterminate system. Okay, so that's something new for the indeterminate system, right? If previously we don't need this, but now for indeterminate system, we have to use compatibility equations. Okay, so now let's look at, for this problem, how can we solve it? Okay, so we already said we have N1, right, minus N2 equals to P1. Okay, that's the first equation. Now the compatibility equation. So I'm just writing com for short. Okay, compatibility. Okay, so we say either the delta 1 and the delta 2 value, right, that equals to delta of the middle point. Okay, or we say the delta total is delta 1 plus delta 2 equals 0, right? And that's our compatibility. We can use either one. This is basically the same thing. It's just depending on which view you're thinking about the geometry relation, right? You can think this way or you can think this way. Either one, that's give you the equation. Okay, so now let's translate this into the expression so we can solve this problem. Okay.
On that first equation of compatibility, is that elongation 1 equals absolute of elongation 2?
Yeah, so basically you can write this way. Okay, if you look at this structure, Okay, so because the middle point there, they're connected, right? If we move delta C to the right, point C move there. So the bar 1 is getting elongation. Bar 2 is getting compression, right? So we can basically, if you don't like the absolute value there, it's hard to do the calculation. So we just write it equals negative delta 2, right? That equal delta C. Okay, or you can write this way. So I write delta 1 equals to delta C. Okay, and then delta 2 equals negative delta C. That's maybe an easy way to express it, right? So the first one elongates that much. The second one has to be compressed that much. Right, this may be an easy way to think about it, right? So whichever way, so you have 3 ways of thinking about this problem, right? So you can think of either use this one, or you can use this one, or the previous one, right? So see here, I write 4 equations. They mean the same thing, right? Because from here, if you have this one, right? This one, you basically can get delta 1 plus delta 2, what? Equals 0, because, right? Because delta 1 equals negative delta 2. So they actually mathematically, they mean the same thing, right? But when you look at the problem, you can sometimes people think this way, from that angle, you think another way, but mathematically, they're the same. Okay, now what's delta 1? We said delta 1 equals, right? The equation we learned, elongation is the N1, L1, right? Then E1, A1, right? Let's assume they have the same material, constant. A1, actually, the area from the figure looks like different, so you have A1. Now delta 2 equals to N2, L2, all right? Then E, assume same material, A2. Okay, now this is the equation about elongation, right? That's what we learned, what we call elongation equation. Well, it's basically about the deformation, right? Okay, so now we have the equation of equilibrium, give us one equation, and the compatibility give us one equation. Now elongation actually link the 2 equations because it links the elongation to the n. Now we have 3 set of equations, so we can combine and solve it, right? You can do many ways, right? Gauss elimination, that's the easiest way, right? So you can replace the variables. Okay, so for example, let me just try one way, and then there are many ways you can solve it. Okay, for example, I can just, based on this one here, right? So I can say, so I can say N1 equals to what? EA1 and over L1 times delta 1, right? So from here, I can say, N2 equals to EA2, then L2, and then delta 2, right? So I'm just express N in terms of delta, right? Okay, so now I can take this back to here, to equation 1. Okay, so I get, so basically taking, if I'm taking this one, let's call this one 1. Okay, so here's the set 2. And then here's the set 3. And here's number 4, right? So taking 4 into 1. Okay, so what do we get? N1, so that's EA1, L1, then delta 1, right? Minus N2, N2 is EA2, L2, okay, delta 2, and that equals to P1, right? Okay, now what's delta 1, delta 2? Here, there's delta C, right? So I can basically get what? So it's EA1, L1, Okay, delta 1, that's delta C. Okay, then minus this one, delta 2. So basically become plus EA2, L2, and then delta C equals P1. Okay, so from this, now I can actually get delta C, right? What's delta C? Will be P1 divide all this thing, right? So we have EA1, L1, and then plus EA2, L2, right? That's it. So now I find out delta C, and that answers my question, right? What's the point me moving? Oh, you say, no, I want to know the N1, N2. Okay, but once you know delta C, can you determine N1, N2? Yes, right? Remember, initially we asked the question, what's N1, N2, right? Okay, you say, oh, find the delta, then go to N1, N2. So now I found the delta C, so I can take it back here, and then I get N1, N2. Take it back to number 4, right? Okay, as I said, solution approach is not unique. You can always do different way, right? For example, I say, yeah, I'm looking at delta N1, N2, right? So I don't care about delta C. So can I quickly find the N1, N2? I say yes. Okay, because I know this relation, right? Okay, so what I know is delta 1 equal negative delta 2. So I can take 3. Taking equation 3 into, okay, number 2, what I get. So I know, okay, this is equal to negative, right? So what I have, it will be N1, L1, EA1, okay? And that's delta 1, right? Delta 1 equals to negative delta 2. Delta 2 is this one, negative N2, L2, and EA2, right? Or you say, I can take it into this equation, right? This is the same, this equation, right, of the number 2. So basically I have N1, L1, EA1 plus N2, L2, EA2. Add together must be 0. Okay. So E can cancel, right? So I get another relation. Let's call this equation number, this is number 5. So we call this number 6. Okay, so number 6. So 1 plus number 6. Then you can get N1, N2. Right? Because equation 1 is about N1 minus N2 equals P. So that gives you. And equation 2 give you the relation between N1 and N2 here, right? So what you have is N1 from here. You have N1 equals to negative N2, right? So L2 over L1, and then A2, and then here's A1. So that gives you the relation between N1 and N2, right? So you can take A1 back to here, to equation 1, so you get N1 and N2. That's another approach of solving, right? So there are many different ways. Once you have a sufficient set of equation, right, you can just take one into another, substitute a variable, and then reduce to one variable, you find it. So you take this back there, so you have, this will be N1, right? So you have negative N2, right? And then the suppose time, put it, make it bigger, N2 times this one. So you have L2A1, L1, A2. Okay, this is N1, right? Then minus N2 equals to P1. Okay, so now N2 only variable. So you can find out the N2. Once you find the N2, find N1. Right, so problem solved. Okay. Any questions? Anyone question? Just unmute yourself. Okay, if no question, someone, okay, go ahead.
So at the end there, did you just substitute N1 into the equation?
Yeah, so I substitute this one, take it into 1. So I get this equation at the bottom there. Substitute the N1, right? N1 I can replace with that expression.
And that was from equation 1 on the previous slide, right?
Yeah, the equation 1 was from
there.
here, right? From the, based on what we get, equation of equilibrium here. This is the relation we got.
Yes, sir. Yes, sir. Okay, thank you so much.
Okay, so now let's go back to this process, see how we solved this problem, right? So we basically try to make the cut, right? Draw the free body diagrams and write the equation of equilibrium. But we found out, yeah, we only have one independent equation of equilibrium equation, right? We can use, and we have 2 unknowns. So that come from, yeah, it's indeterminate. So then we say, yeah, let's look at the deformation, right? So the deformation of bar 1 and 2, they have to somehow match each other, cannot be randomly deforming. Otherwise, it will break apart maybe at point C, right? So we say if the structure is intact, everything is in equilibrium, they must have certain relation. And then we find, oh, they have to, this point C have to move, right? And that the one get stretched, another get compressed, and they have to be the same amount, same magnitude, right? And that gives us compatibility relation. So then we say, okay, write the compatibility equation, then combine with how each one elongate, right? So that, because that elongation equation, then the link the deformation to the force, right? So we get everything linked together. And then we combine all these 3 set of equations, right? We solve it, and solve it, you can have many different ways, but that doesn't matter as long as you solve it, right? So the key is this first equation, second equation, and third equation. That's the basic equation we lay out. Okay, so then we solve it, we got this answer. All right. So in summary, right, the key is you make the cut, and then you draw the free body diagram, and then you basically solve it. Okay, so let's summarize it before we go to more examples. Okay, so basically for indeterminate bars, we know it's indeterminate because you have redundant restriction. There will be redundant reaction forces. Okay, and that redundancy is needed for structural stability or for functional need. Okay, so it's basically the key is the number of equations of equation of equilibrium you can write is smaller, right, than the number of reaction. In this case, it's force, right? So it's reaction forces, right? Or the including the internal and internal force. Okay, so it can be this reaction force, that's R, right? We always call it R. So R or N, right? They have too many that you cannot determine by the equation. Okay, as how to solve it, we summarize it. You make the cut. Okay, and then you draw the free body diagrams. Okay, and then you write the equation of equilibriums, right? Equations of equilibrium, right? There can be multiple equations, right? And this can be multiple one, right? So x n, right, times this can be multiple one, x n. Okay, and this can be multiple one as well, right? And then you have to write the compatibility equation. and it can be equations, right? So this can be multiple one as well, right? And then you solve the equations. Solve all equations, right? So you have to combine. You can actually combine the equations. It's not simply just solve the equation of equilibrium, right? So it has to be combined. So you have multiple equations, become an equation group, a set of equations, you solve it together. Okay. So to summarize what we have here, I have an acronym here. So I call, okay, so this is the free body diagram, right? Start with that. Equation of equilibrium, and then compatibility. So I call it Fed.com. And that's basically the approach, how to solve the indeterminate problems. All right. So if you talk to the student, took my class before, they all know what's Fed.com. That's basically the approach to solve an indeterminate problem. Okay. And this is actually a very general approach. Here we talk about elongation bars, right? The indeterminate. Later on, we talk about shaft, indeterminate shaft. It's the same as Fed.com, right? And then we have the beams, same Fed.com. All right. So all the indeterminate structure, this basically give you an outline approach, right? A roadmap, basically how to solve this kind of problem. All right. Okay, can you remember Fed.com? Whenever you see an indeterminate problem, okay, Fed.com, just follow the steps, right? Okay. Of course, you have also make the cut, right? Make the cut just help you to set up free body diagram and write the equation of equilibrium. So cut is important because you want
Professor,
internal force or internal movement. Yes.
Yeah, once again, how do you know whether you have the indeterminate problem?
Okay, how do you know indeterminate or it's a determinate? Okay, good question, right? So we have a quiz, okay? So you can start doing make the assignment available. You can look at it. There are several structures you can judge there, okay? But here, just very quickly, okay, I can give a couple of examples. For example, right? So if I have this structure, okay, one load here, one segment here, right? You have all the load. So P1, P2, P3. You have so many load, and maybe even there is a P4. Okay, but the the restriction only on this side. So there is only one R here. Is this determinate or indeterminate?
Determinate.
Determinate. Because you have only one restriction, right? Doesn't matter how many load you have. The load is known. So the equation of equilibrium, you can write, let's say in this case, it's only one, but you have only one unknown. So the reaction, how many reaction forces, that's the initial way saying you use to judge determinate or indeterminate. Okay. Yeah, so this is a very good question. Now let's say what we just showed there, right? So if you have say a bridge, okay, so if you have a load applying here, or you may have two loads there or three loads there, okay. Now how many reactions do you have? You have RA, RB, right? So two unknowns. So is this determinate or indeterminate?
Indeterminate.
No, it's determinate. Because how many equations you can write? In this case, you can write two equations.
Ah, so it's when you have
You
more.
have a movement equation. They have to be
So-
balanced, not to rotate. Two unknowns, two equations, perfect. So it's determinate. Okay. Let's say another situation. If I have this one, so I have a wall. Okay. So I have one bar here, another bar here, right? Or maybe another bar here. Okay. So then I have a weight applying here. Now, is this determinate or indeterminate?
Indeterminate.
Indeterminate, because in general, you don't know the reaction here, right? So you have the R1, R2, and then you have R3. Or you can put it vertical, doesn't matter, right? So you have 3 unknowns. And the equation you can write is only in the x-ray 2 equations, right? So you have sigma Fy equals 0. Right? And sigma m to a point, let's say this point O, to point O equals 0. But you have 3 unknowns. So it's indeterminate. Right?
So it's
So
when you have
that's basically you write the equation of equilibrium about the system, right? And then see how many unknowns restriction there and how many equations you can write. In general, 2D, you can write 2 equations. The reason we can only write 1 because this is a special case. Everything along one line. On one line, you have only 1 equation. The moment, right? It's all the force align in one direction, one line. So there's no movement. So therefore, no movement equation is automatically satisfied. Movement equals 0. But in general, like this one, you have moment equation plus the force equation. Right? Okay. So that's how you judge it. So I have actually several more examples that's in the quiz. So do the quiz, then you think about it, and then kind of get you familiar with the indeterminate. Okay. So we're going to go over a couple, let's say at least two more examples today. So you'll see the possible indeterminate structure. This way you get familiar with it, right? So you can quickly realize it will be or judge it's determinate or indeterminate. Okay. All right. So remember Phi.com. That's our tool, right? Okay. Let's say we have this structure here. Okay. I have the ceiling there with the 2 cables. Let's say they have 2 same cable, right? Hanging a rigid beam. So this part is rigid. So we don't talk about the beam deformation yet. We haven't learned that part. Okay. So you carry a weight P there. Now, is this determinate or indeterminate? Anyone? Well, you're not sure? Let's write it. So you draw the free body diagram. Okay, so for this one, let's say I select this object here. Select this rigid beam. Okay, so for this rigid beam, sorry, poor drawing. Rigid beam. So I have this reaction here. This will be N1, right? And this one can be N2. Now I have the load P here. Okay, so the equation of equilibrium. What I have? So I have N1 plus N2 minus P equals 0, right? Oh, 2 unknowns. Is that determinate or indeterminate?
indeterminate.
Well, we don't know yet. You haven't write out all the equations, right? So I have a moment equation. So I can write it about this point A, C, or B, right? Okay, now you can pick any point. Let's say I write about C, right? Or write about A, which one you want? Let's see which one you pick. Someone you want to pick? Okay, so this is the sigma Fy equals 0. Okay, someone said, sorry. Sam, you said where?
Point C.
Point C. Okay, so therefore sigma moment to C equals 0, right? So that gave me N1, right? Moment to point C here. So therefore N1 times AC length looks like equal, right? So let's say AC length. Okay. And then that's going clockwise. So I say that's negative. And then plus the N2 times the CB distance, that's equal 0. Well, this is independent from the first equation. So I have two equations. This one direct gave me link between N1 and N2, right? Assume AC, BC, they are the same distance, B. Okay, then this will be the same. So that immediately gave me N1 should equals N2. If they're not equal, right? One is B, one is CB, they're different, then there's certain ratio. So they're proportional, depend on distance, right? But at least this give me a second relation about them, and then combine with the first equation. So I can solve it. I can find N1, N2 from equation of equilibriums, right? Or the equations of equilibrium, two equations of equilibrium. So therefore, this one is determinate. All right, so we don't need the fed.com issue. We can directly, you're applying load P here, right? You can figure out what's N1, what's N2. So you can find out what's the elongation 1, what's the elongation 2. Then you can find out how much is this point, this beam going to move, right? If they're the same beam, same distance, then they will basically stay flat. If somehow this two elongate differently, they will tilt a little bit, but still you can determine how much they elongate. So you can determine how much tilt it will happen to the rigid beam. Okay, so this is determinate. Okay, because I have enough equation determine all the unknown reactions, right? So the N1 is basically the reaction here, right? N2 is the reaction here. Okay, so it's determined. However, now if I want to make the structure stronger, so I can add another beam here. So this is a different beam. I mean, not beam, sorry, a bar here, right? Different cable. Okay, if I add a third cable here, okay, this will be a different, either different cross-section or different material, right? Now, this structure become indeterminate because I know I still have two equations, but now I have three unknowns. So I know immediately, yes, it's indeterminate. Okay, so if you have this bar here, 3 bar, that's a structure. Or if I can add more, right? So imagine you can add one more here, one more here, or one more here, right? So in the reality, in the world, real world, you can maybe have 5 cables there. They're different, and applying the load there, right? So that 5 loads, right, unknowns, you don't know how they distribute. The 5 unknowns versus you have 2 equations. So that's definitely indeterminate. All right. Okay, for a little bit easier, as an example, we have limited time. So let's say, look at, we have 3 cables here. Okay, so remember, now it's indeterminate. So first we judge it's indeterminate, right? And it will conform by equations later, right? Okay, so now we know we should use the fed.com. That's the approach, right? Okay, so first, right, I'll make a cut. So I make a cut here, cut here, cut here, right? Or I can just cut it, but basically I'll write the equation of I draw a free body diagram about this rigid beam. Okay, so let's draw it here. So what I have will be this rigid beam. I'll just draw parallel to it, to the side by side. Okay, just okay, this is the rigid beam. So I have this load P applying here. So I have this N1, right, of cable 1. Then I have this N3 of this new cable, right? And then I have this N2, right? So N2, I know N2 is N1 immediately. Or maybe I don't know, right? Can be different. So let's, for general, say, situation, we just don't use this relation yet. Okay, because if there are 2 cables same, right, this whole thing is symmetric, so I know N1 quickly. I can judge N1 equals N2. But let's say the cable maybe even sometimes different, right? So let's just assume in general situation we can have N1, N2, N3. Okay, so this is the free body diagram. Okay, so the part. So that's a free body diagram. All right. Now equation of equilibrium. So we can write the equation of equilibrium. Okay. Equation of equilibrium. So I have sigma Fy equals 0. So I have N1 plus N2 plus N3. That equals to P, right? Or net minus P equals 0. Okay. Then the moment. Okay. So moment to some point equals 0, right? Okay. So we can use the same to C equals 0. Okay. So I have the same equation, then N1, okay, negative, right, times this distance, let's say B, and then plus the N2, okay, times this distance CB is the same, and that equals 0. Okay. All right, now what's the deformation equation, right? The Fed.com, the D part. Okay. Here, the beam is rigid, right? But that force N1, N2, N3 going to pull the cables. And that cables, or 3 cable will get elongated, get pulled, right? So the first cable, delta 1, will be equal to N1 times this L. I guess based on the graph, the L is all the same, right? So this is called capital L. Let's just use the same letter as given here, right? They give you the length. Okay, then the EA is the same material, right? Okay, and then the delta 2 is N2 L, and then the EA, there's the same cable. Now I added cable 3, so delta 3 equals to the N3, right? The same length. Okay, same material, assume, or can be different material, right? Doesn't matter. Or can be the area is different, right? So let's call it E3, A3. It may be different, right? Okay, so that's the thing, right? The Fed FED part. Okay, now we need the compatibility. Okay. Are you convinced this is indeterminate? Is everyone convinced this is an indeterminate problem?
Yes.
Okay, then
Yes.
we can go ahead, right? Fed.com. All right, so what's the compatibility? What's the compatibility? Imagine you have this load applied there, right? So you're going to pull it down, right? So this bar initially here, you're going to be pulled down to a position, let's say here. Right? Imagine that going to pull down here. So the beam will move to here. Okay. Now what's the elongation of the first one? Delta 1, right? Elongation of the second bar cable is delta 2. The third one is delta 3. So what's the relation? So here, this is the delta 1, right? From this point to here. Oh. Right? So this is the delta 1. Right? Or I can draw this way. So from here to here, right? That's delta 1. You can draw from here to here. That's one way. Use the other edge, or you can use the middle line, right? So that's delta 1. Okay. So here's delta 2. I'm sorry, delta 3. Right? So here will be delta 2. Right? Because this point, this will just move down. Okay, so now what's the compatibility? How the delta 1, delta 2, delta 3 are related? The
They're all
geometric
equal
relation
0.
between delta 1, delta 2, delta 3. Yeah, sorry, someone have asked.
They're equal to 0 when we take the summation.
They are, why they equal to 0? When you push it down, pull it down, right?
Oh,
So
yeah,
they
yeah.
move down, right? So they're moving, right? This beam move down this distance. So what do you have?
Are they all equal to each other?
They are equal to each other, right? Because all the point has to move the same distance, right? So therefore, what you have is delta 1 equals delta 2 equal delta 3. That's a relation. That's a compatibility equation. So actually, these are two equations, right? So delta 1 equals delta 2 equals delta 3. So basically, two equations. I can just write it here, right? So now you basically we lay out all the equations, the equation of equilibrium, deformation equation, and the compatibility equation. So now we can just go combine all those equations, so we should be able to solve. Okay. So the first step to me, I would recommend, right? So draw the free body diagram, and then lay out all the equations before you try to solve it. Just lay out the equations, and then you solve it. Okay, because you lay out the equation like show me how you know how to do it, right? You lay out the equations, right? And then you solve it. You know, there is a chance when you solve the equations, you can solve it wrong. But that's just, you know, you calculate a number wrong or something, right? It's less a mistake than you don't, if you don't show this layout, this equation, then I don't know whether you know how to solve it now, right? You lay out the equation, so you show me, yeah, you know how to solve it. It's just somehow when you calculate the one wrong, so the wrong answer, that's less a mistake, right? Anyway, okay, now let's solve it together. That's the next thing, right? The solution part. Okay, so this equation, what do we get? So basically N1 equals N2, right? Okay, so the equation of equilibrium, we solve it, we can simplify it. So N1 equals N2. Therefore, take it into the first equation. So we have 2N1 plus N3 equals 2P. So we have only two unknown forces, N1 and N3, because N2 is the same as N1. Okay, so the elongation equations, we have all the three. You can say this relation, take it into this relation. So what do we have? We know N1, this is the same, right? So this two the same. N3, I'm sorry, wrong one. So this two the same, right? N1 and 2 the same. So they just basically repeat each other. Okay, so we have, so automatically delta 1. So automatically, right, delta 1 is equal delta 2, and 1 equals N2. That's already there. So what do we get here? So basically, we can use what we need. It will be delta 1 equals delta 3. Right, because delta 1 equals delta 2, that's already satisfied. Okay, so that gives us, all right, delta 1 is this one, delta 3 this one. So we have N1 L over EA. Okay, that's supposed to equal to delta 3, that's N3 L. Okay, then the E3 A3. All right, so that gives us a new equation. Okay, so let's call this equation 1, this equation 2. Now combine those two equations, we can get N1, N3. Right? So the solution is not that complicated. Right? Okay, so shall I just leave the solution to you, right? So follow to solve it. Okay, so let's save some time. We have only 15 minutes left. I want to go over another example. Okay. I'm sure you can solve this equation, right? Two unknowns, N1, N3, N1, N3, two equations, solve it. Okay. All right. Any quick question about this example? No. All right. So let's look at the next example. Okay, so here's one, actually, I think it's in the textbook, right? So you have a bar in the middle and then two cables on the side. So that's an indeterminate structure, okay? So I will not go over this one, but I would rather go over this example, okay? So here is a situation. It's kind of different from every single line in the y direction. Okay, so here is you have a rigid beam. Okay, so this is rigid. Against rigid, we ignore this beam deformation. Okay, so you have this support by two cables. All right, the two cable are supported hanging there, right? And this point A is a pin support. Okay, so it's pinned. Okay, by pinned, we basically means, right, it's stuck there, cannot go anywhere. It's like a joint, right? So but you can freely rotate. So there is no reaction moment. What you have will be reaction force. So that could be RAY. Okay, so the RAX is actually 0 because there's no load in the axial direction, right? So you can ignore that X there. Okay, so basically pin support means no movement, free rotation there. Rotation movement is not restricted. Okay, but there is a force RAY. Okay, so I want to emphasize there is a RAY here because many people, when solve this kind of problem, either in homework or exam, they forgot to label the RAY, and therefore, if you ignore the RAY, then the system become determinate, and basically your solution will be totally wrong. Okay, because if you consider RAY, then this system is indeterminate. Okay. Why? Let's first confirm this is indeterminate. Okay, so if we draw the free body diagram of this beam, so this beam here. Oh, excuse my drawing. Let me make it a little bit better. Okay, so right here. Okay, so here's a joint connection. So I draw a circle here, just remind you. So what you have will be reaction force RAY, right? Okay, now this cable CD, going to stretch it. Here is N1. Okay, then the cable EF, you're going to stretch it. So you have N2 here. All right, and the load is here, P. So basically I made the cut here and here, right? This way N1, N2 show up. Right. So the cut is just make the force in the cable, internal force in the cable show up in the free body diagram. So I can write the equation about it, right? So then I can find it. Okay. So for this one, now let's write the equation of equilibrium. Right. So this is the free body diagram. We already have it. So what's the equation of equilibrium? We should have sigma Fy equals 0, right? Then the sigma m to a point equals 0. Okay, sigma Fy equals 0. Let's finish it. So what do you have? You have RA y plus N1 plus N2, right? Minus P equals 0. How many unknowns? 3. 3 unknowns, right? Okay. Now moment equation. So let's write the moment equation, right? You have one independent moment equation. So let's say we came to point A. Why select point A? Because this way the moment of RAY is 0, that disappear, right? So the immediate what I have. So to point A, so this point, this direction we call positive, right? The moment. Okay, so I have N1 times B, then plus N2 times 2B, right? And then plus, actually minus, P is the other way, times 3B. That equals 0. Right? So two independent equations, sigma Fy equals 0, and then sigma m to A equals 0. That's it. Only independent equations I can write, right? Or in the x direction, nothing. So no, it's 0 equals 0. Now, how many unknowns? 3. You have RAY, N1, N2, 2 equations. So it's indeterminate, right? Or you can say, if you look at just this equation alone, right? You have one equation, but the two unknowns, right? N1, N2 in the second equation. So still redundant reaction there, right? So you cannot find the internal force or the reaction forces from the equation of equilibrium alone. So it's indeterminate, conform, right? So indeterminate. Okay, that conform by the equation. All right. Okay, so indeterminate. So Fed.com come to play. All right. So Fed.com, make the cut. I cut the cable, draw the free body diagram. That's already done. It's here. Right. So therefore, I write the equation of equilibrium. Yeah, I have it here. Okay. Now, next, Fed.com, right? So the D, deformation, the D part, the deformation. Okay, or often I just write the word D there. Okay, so what's the deformation equation? We say the beam is a rigid, so beam doesn't deform. So what deform is the cable, right? So the two cables, they deform. So the first cable, CD, elongate because the N1. So you have this L1. Okay, so let's assume the same material. So you have the EA, or you can different, then you have E1, A1. All right, and then the second cable, elongate deformation. So basically, we talk about the cables, right? Only the cable deform. So delta 2, that's N2, L2, EA. All right, that's deformation. Okay, so basically cable 1 gets stretched by N1 a little bit longer. Cable 2 gets stretched a little bit longer because of N2. Now, how those two match each other? What's the compatibility? How they compare relatively, right? Move relatively compatible to each other. Or the geometric relation, right? Between them. So basically it's geometry, right? The compatibility is the geometry, right? It's relation about the deformation geometry. Okay, so how does this thing deform? Now, because you have this restriction at point A, okay, point A not going to move. It's a joint, it's a pins. So when you pull at point B, this whole beam won't move down like the previous example. Instead, this one will actually rotate, right? So B can freely move down, but A is not. So initially you're here. Okay, let me draw with a different color. Okay, initially your center line is here. Okay, now if I pull it, it will move down. So this point can freely move to, let's say, to here. I'll make it bigger so you can see it's actually, remember, we talk about tiny deformation, right? So this move down here. And then this beam is rigid. So therefore, it cannot be curved. It has to be a straight line. So what do you have? It will be a straight line here. So this point move here, right? So this point B going to move to this here. Then this point here have to be moved to here, right? So this will be the delta 2, right? Okay, now this point initially here, it must move down to here. So this is the delta 1, right? So when you pull this thing, now the first one cable and second cable, they have to deform differently. You have to pull the cable EF stretch longer. The cable CD actually deform less because this whole beam rigid there, right? Is pinned on the left at point A, has to be rotating, right? Okay, now what's the relation between these two rotation? I mean the two deformation here, elongation, delta 1. Now notice here, they just all rotate the same angle. If they call this angle alpha, right? So then what do you have? So the delta 1 must be the length B times this angle. Delta 2 must be the 2B length times this angle, right? Or you say it should be tangent to theta, right? Remember, we talked about small deformation. So theta is tangent to theta, right? Okay, so basically they have to be proportional, right? Or in other words, so your delta one, right, divide by this length b, divide this edge here. This is b, right? And then must be equal to the delta two to the edge 2b. So this two must be proportional because it rotates the same. That's the compatibility. All right. So what I'm drawing here, the red part, is just showing how this beam moves, right? It moves down an angle alpha. Right? Actually, I use theta here, so it's supposed to be theta, not alpha. All right. So rotate by angle theta. When it's rotate, then the delta one, delta two has to be proportional, and that's the compatibility equation. All right. So with that, now we have a third equation, right? So the first equation, this is the second equation set, and then this will be the third equation. That's the compatibility, right? So now we can solve it, right? As I said again, you have many different ways of solving it, but this basically give you the same solution mathematically, right? Different approach of solving three equations as I said, right? You can eliminate the first variable or you eliminate the second variable, but eventually you get all the variables. All right. Okay, so let's quickly, we can actually give one approach to solve this three equations. Okay, so I have this one, right? So I can take it into this equation 3. So taking, this is just one approach of solving this set equation, right? So I'm taking 2, right, into 3. Okay, so what I get? So delta 1 over B1 over B, right? So delta 1, that's N1 L E A, right? And that's divided by B equals to delta 2, that's N2 L2 L1 L2. I think L1 L2 actually, just look at it, it's the same. Let's just use it there, that's fine. So E8. Okay, and then divided by 2b. Okay, so if let's assume L1 equals L2, then immediately I get N1 will equals to half of the N2, right? If L1 is not equals, then there will be ratio proportional with L1, L2 ratio, right? Okay, so with that, I can take this into equation 1, right? I can solve it, right? Because so N1 equals half N2. So I have the N1, that's half N2. That's N1, right? And then times B plus N2 times 2B. And that equals to P times 3B. So B can cancel out, right? So B here, B here, B here, right? So what do we have? So we end up here. So we'll be half N. So basically I have 2.5 N, 2.5 N2 equals P. So immediately now I got N2. Once I have N2, I got N1, right? I know N1, N2, so I can calculate delta 1, delta 2, right? And actually you can calculate how much this point move as well. There's delta B, right? Okay, so basically now this problem solved, okay? Our time is up, but I just want to quickly show the last slide. So we'll talk more next time, but here I just give you type of structures, right? Indeterminate structures. And that we use very common here called the truss system, right? Or truss structure, or just called trusses. right? You can see here either a bridge, they have many of the beam bars connected, or the scaffold, or the pieces in the wood in the building. So this all indeterminate structures. All right. Okay, so I'll see you all next time.
Professor,
Yeah.
when will this video be uploaded?
So I'll try to load it by tonight. Let me see where is the
Okay. Thank you so much. Have a great day.
Thank you, Professor. Have a good one.